Hello, and welcome to this video on the PWM pin. In this video, we will look into pulse width modulation, commonly known as PWM, and its critical role in computing systems, especially in edge devices. Let's start with an introduction to PWM. PWM is a technique which is used to control the amount of power delivered to an electronic device by breaking up the power signal into distinct parts. Instead of delivering a steady output, PWM rapidly switches the power between fully on and fully off, effectively creating an output analog signal. In the diagram on this slide, we show this for three cases. The broken green line denotes the period when the pulse oscillates. So if a signal is 100 Hz, it will oscillate 100 times each second, or the time period for each oscillation will be 0.01 seconds. Now, duty cycle denotes the amount of time in percentage that the power is on in each time period. So if the power is off for the whole of this time period, it is denoted by a 0% duty cycle, as shown in part 1 of the diagram. If the power is on for 50% of time and off for the rest, it becomes a 50% duty cycle, and the effective output voltage becomes 2.5 volts if the reference voltage is 5 volts, or 1.65 volts if the reference voltage is 3.3 volts, like for Arduino Nano. Similarly, for a 100% duty cycle, the power would be on all the time as shown, and the effective output voltage would simply be 3.3 volts and 5 volts. And so, you can create almost any output signal voltage by modifying the duty cycle, thus making it similar to an analog signal. This working also explains why PWM pin is coupled with a digital pin. PWM pin is nothing but a digital pin with added circuitry to provide PWM functionality on the edge device. The device's datasheet will contain information about which pins have PWM functionality. On the pinout diagram, they are usually denoted by a tilde or the wave symbol. Now that we know how a PWM pin works and how to identify it on the pinout diagram, let's understand why we need it in the first place. Why not connect the external device directly to an analog pin? The reason is that many digital systems, like microcontrollers, cannot directly output analog signals. They would need a digital-to-analog converter, or DAC, which would increase cost and the size of an edge device, both of which are highly undesirable. PWM, on the other hand, offers a flexible way to simulate an analog output using digital means. This makes PWM particularly useful in situations where you need to control the power for devices that cannot easily be controlled by analog signals, such as LEDs and motors. Finally, let's look at PWM's applications. You can use PWM for a variety of applications, like controlling the brightness of LEDs, the speed of motors, or even the temperature in heating elements. By adjusting the duty cycle, you can control how much power these devices consume over time, which can be crucial for battery-operated edge devices in AI applications. And that is all for PWM. If you want to learn more, I will add links to some resources related to the PWM in the resources section. In the next video, we will talk about analog to digital converters, or ADCs. See you there.